Welcome to another lecture on ECEN 215, Principles of Electrical Engineering. Today we're going to talk about steady-state AC signal analysis, and we're going to focus on nodal voltage analysis using that method in the AC signal analysis domain that we're now talking about. So this is a group of two lectures, lecture dealing with nodal voltage, and then we're going to follow up doing mesh current. So everything that you've remembered learning in the DC circuit analysis for the method still applies. It's just now we're going to reintroduce complex impedances and phasors to that. As such, we're going to first just do a real quick review on complex impedances because this is critical for us to do the circuit analysis. So again, impedance, the actual definition is the effective resistance of an electric circuit or components to alternating current arising from the combined effects of ohmic resistance and reactance. So what we're talking about here is we're now using alternating current or alternating voltage that has a sinusoidal component, and it has a frequency and is periodic in nature. And it also has possibly a phase shift. So as we've learned with voltage and current here, we can represent it as AC signal. We can represent everything using cosines, and just by changing the phase angle, we can cause it to be a sinusoid by subtracting 90 degrees or any phase angle thereof, and of course at any frequency. So there is resistance and reactance, and we also learned this is an imaginary or a complex number, where the resistance is the real component measured in both ohms, and reactance, which is the imaginary component. As we discussed the other day, this is represented by the J term of the complex number. And again, all of the units are in ohms. Ohm's law still applies. It's just now instead of R, we're going to use the letter Z to represent that this is a complex impedance instead of just ordinary resistance. So we have V over I is Z, V over Z is I, or V is equal to IZ. So if you've learned that equation, have mastered it, then you are all set. You just have to replace the letter R with the letter Z. So the impedance of inductor, again, this is just review from what we had before, is just equal to omega L, where omega is the frequency in radians per second. And if you're given frequency F in the sense of hertz, like 60 hertz or 100 hertz, then that is just 2 pi F. So just take 2 pi times the frequency, and that gives you omega. In a case of an inductor, you're given the inductance measured in henries. So the impedance is omega L with a phase shift of 90 degrees in the polar form notation, or written in the rectangular form or complex notation, we have just J omega L. Notice there is no actual inline resistance. So an ideal inductor is purely inductance, and it's J omega L. A capacitor, by contrast, is similar in that it's 1 over omega C with a phase shift of minus 90 degrees. Again, where omega is the frequency and C is the actual capacitance of the component. In this case, say 1 microfarad. So we have ZC is also in the rectangular form as minus J 1 over omega C. Notice this corresponds that with a positive 90 degrees, it is all purely in the rectangular form, it is a positive J, whereas the minus 90 represents a minus J. And of course, resistors are just simply that, they're resistance. So they have no imaginary component. So again, for review, impedance can be treated like resistors. So if you have all of these impedances figured out, you can add them together in series, just like you would with resistors. So if I had a capacitor, an inductor, and a resistor all in series, and I computed their complex impedances and what they actually are, J omega L minus J 1 over omega C, J omega C for the capacitors, and for resistors R, you can add it all up and you would get a complex number that represents the equivalent impedance. So this is unlike in the lecture we had with the transients before, where with capacitors you had to do things where parallel capacitances were added together and parallel and series resistances were one over the reciprocal, and of course inductors and resistors operate in the same fashion. This is treating everything as an impedance, so you have to go through and compute the impedance. So in parallel impedances, again, just like with parallel resistors, you go through the same mathematical process, one over the reciprocal, or in the case of just two impedances in parallel, it'll be Z1 times Z2 over Z1 plus Z2 would be the equivalent impedance there. You can also perform steady state circuit analysis just like you would with steady state DC analysis with resistors, but instead you're now working with impedances. And that's exactly what we're about to review now. So here we have a circuit. It's a simple little circuit. It has three components in series plus a power supply, so four total components of the circuit. And we are given a Vs, and we're asked to determine this loop current here, I of t. That's the current that's coming out of the power supply and returning. So simply, what is the current going through all of the components? So how would we do this? So if these were resistors, we would know exactly what we would do. There's various methods. We could do mesh current analysis, which we'll talk about doing that in AC analysis in the next lecture. But this is actually fairly straightforward. All we really need to know, if this was three resistors in series, quite frankly, what we would do is add everything up, get the total resistance of the circuit, the R equivalent, and just take V of S divided by R, and it gives us I of t. So we just simply use Ohm's law for this. Well, we can do literally the exact same thing now, except it needs to be the impedances that we add together. So if we know this impedance, and we know this impedance, and we know this impedance, so we know the 100 ohm, the 0.3 Henry, and the 40 microfarad capacitor, if we know the equivalent impedance, then we would know this circuit. So let's go ahead and do that. So first step is to convert everything over into the complex form and phasor form. So as you notice here, we've turned our power supply, which was 100 cosine 500t plus 30 degrees, we can went ahead and converted that into the phasor form, which is just simply 100 with a phase shift to 30 degrees. The omega is just written down on kind of on the side here. The omega is 500 in this case, and that's going to be used in computing these other values. So the resistor was fairly easy. It's 100 ohms. There's not much to it. ZR is equal to R. ZL, as we learned earlier, it was J omega L. So omega was 500, and we have 0.3 Henry, so 500 times 0.3 leaves us to J 150 ohms. For the capacitor, we have 40 microfarads, so 40 e to the minus 6. So we have that 40 e to the minus 6. Let me enter that in my calculator here. And omega 500, but we have to take 1 over x of that, and that gives us 50. So 1 over omega c is 50, but it's minus j, so minus j 50 ohms. So we have we have the ZR equal to 100 ohms, the ZL equal to j 150, and the ZC equal to minus j 50. And to go ahead and get this actual value, the Z equivalent, we just need to add them together. So let's go ahead and do that. So we have R plus ZL plus ZC. So again, since we're adding in the complex domain, all the real values add, and all the imaginary values add separately. So we end up with 100, because this is the only real resistance in the circuit right now, plus 100J, because the 150 minus 50 added together just becomes 100J. So now we need to get the current. And the current is simply the same as before, just if this was three resistors, Vs divided by Z equivalent. We've got the 100 over 30. We got that from, again, the 100 cosine 500t plus 30 degrees. So we had this. And we got this phasor form of Z equivalent from this here. And we got that by taking 100 over 100 So the imaginary over the real and taking the arc tangent, and that gives us 45 degrees. And then we get the 141.4 magnitude by taking the real squared plus the imaginary squared and taking the square root of that, and that leads us to 141.4. So if you need help on converting again, going back and forth between rectangular and polar form, go back a couple of lectures when we introduced phasors, and those slides go over that in detail. So that's why it was important that you master going back and forth in the various forms and using this. Because now we simply have a voltage divided by an impedance, which gives us current, which mathematically we have two phasors in polar form that we need to do division of. And again, we learned that in the introduction to phasors. What we have to do is take 100 divided by 141.4. So we have that. So let's do that real quick. We end up with 0.7072 as a magnitude. And we simply need, since we're doing division, we just need to simply subtract 30 minus 45, which leads us to a current of 0.707 with a phase shift of minus 15 degrees amps. If we wanted to convert that back to I of t, because that's what we were asked for, we were asked what is I of t, then we just need to push this back into the cosine domain, time domain form, which is 0.707 magnitude of amps, cosine 500t, because this is our original omega, so that carried through the analysis undisturbed, t, and of course the phase shift of minus 15 degrees. So now we're actually going to use nodal voltage now. So that method before was just simple Ohm's law, basic methods of circuit analysis using the equivalent. Here we're going to use nodal voltage analysis. At this point, again, would have you, since we're going to have a homework review lecture after this sequence of lectures that we have on AC signals, this will be the time to start coming up with a list of questions out of the homework that is confusing, or you're unsure how to work, or something you're unsure of something in a method. This is the time to start adding those questions up and emailing me so that we can start having a discussion over specific problems. And of course, the Q&A sessions is an excellent place to ask these questions and have us work problems that you're unsure of. And the same thing with the office hours. So please take advantage of that in these classes. So here we're asked to determine V1 of t. Now in the same process, it's kind of already pre-done this for you. The nodal voltage method, if we're asked to determine, for instance, the voltage here across this 10 ohm resistor, this first step is to define a reference node. The reference node was for this particular problem was already defined for us. It's right here. So you pick a reference node. And again, a tip for picking a reference node is usually to find where there's the most common connections, basically the node with the most connection points to the elements. Usually it's fairly obvious, as like in this case where we've got these two current supplies and this resistor and this inductor are all connected together, and it's all common tied here at the bottom, has the most connections. So that was the most logical place to put the reference node. And obviously it also made sense, particularly since it was looking for this particular node, that it's easier to give V1 of t instead of V1 minus a V3 of t if this was, say, the reference node over here. Again, the reference node can be any position as long as it is the node that all of the analysis is done by. You cannot have multiple reference nodes. So this is node 0 as it's known, or the reference node. So we have that as our basis point. And then of course the next step in nodal analysis is assign the nodes, which was already done again for us here. We've called this node 1 and this is node 2. So that is the problem that we have. We've got this amp current supply here of 2 amps sine 100t. Notice it's a sinusoid, not a cosine. So it's sine 100t. So we're going to need to convert that over to a cosine so we can use our phasors. But this is the power supply 1, and we have another power supply over here, a current supply. That's 1.5 amps cosine 100t. Notice the fact that these frequencies are the same. This is very key to this part of the analysis, that we're analyzing the same frequency. Else you would effectively have two different types of circuit analysis. all the problems that we're looking at here for this particular exercise and everything we're doing for AC analysis is assuming the same frequency that's going through the circuit. So the omegas should match and do. So 100T. Omega is 100 in this case. Now you will have problems probably on the test, and then if there are any future quizzes or anything, you will see instead of omega, you might be given F. In the case of 100, the actual frequency here, just for our own exercise, is divided by 2 divided by pi, which is approximately 15.9 hertz. So if I gave you a frequency of this circuit was, say, close to 16 hertz, 15.9 hertz, then you were asked what is omega, you would do 2 times pi that, and you would get approximately 100 for that. If it was 16 hertz, it'd be a little over 100. For 15.91 hertz, you would get 100 radians per second. So that's our first step. So we're being asked here to write an equation and determine V1 of t. Now again, it's very important to know what is being asked for. It's not being asked for the phasor V1. You're being asked to give us V1 of t, which means that there's at the very end of this analysis, since we're obviously going to be using phasors to do this analysis in complex impedances, the very last step is to take the answer in phasor form and convert it back into terms of cosine. So first thing we did is we convert over our values into the phasor domain. So we start with our sources first. We had 1.5 amps cosine 100t. So immediately we know we have a phase angle of 0 degrees because we didn't add any angle to the cosine. And we had omega equal to 100. Now in the phasor form, we don't store the omega, we just make a note of that. And so this one just becomes 1.5 phase angle 0 degrees amps. Over here we had 2 sine 100t, but again phasors are based on cosine, so the transform of sine to cosine is just equal to a cosine of minus 90 degrees. So we end up with the omega still 100t, or 100, and then we end up with a phase shift of minus 90 degrees. So this is now in the cosine form. And of course, it's 2 amps. So 2 amps of phase shift of minus 90 degrees. So now our sources are transformed. The resistor stayed the same, 10 ohms. And we have a capacitor that was 2,000 microfarads. And let's go ahead and convert that over. And we got minus J1 over omega C. And that gives us minus J5 ohms. And for the inductor, it was 0.1 henries. And it's J omega L. And so we end up with J 0.1 henries times 100 ends up plus J10. So that's how we have all the impedance values, and we have redrawn our circuit here, as you can see, exactly now in terms of impedances. Again, sometimes students find just placing a box here instead of the actual component sometimes helps them visualize this a little better. I have left them in the actual components just because that's what they are. So now we're going to do circuit analysis. We have everything we need to do circuit analysis. The nodal voltage method here is exactly the same as what we used here several weeks ago in the earlier topics for doing DC circuit analysis. Nothing has changed with the method. Now I will make a point here that if you are confused on how to do nodal voltage analysis in the DC circuit, you're going to be very confused doing it in the AC method. So even though it's the same exact method, we're now introducing all this new math using phasors. And so I would recommend getting comfortable with the DC circuit analysis using resistors first before really jumping into AC circuit analysis. There's no reason why you can't just jump in with AC, but it would be easier to practice again with the DC circuit analysis. Make sure that you're completely comfortable with doing that before really jumping in here with the AC, because again, you're now introducing complex arithmetic into it. So with that being said, let's start the circuit analysis here. So again, I like to do leaving current. That means we're using Kirchhoff's current law for nodal analysis. And we've got 2 nodes, V1 and V2, and we have our reference node, node 0 is right here. So everything that's being measured, like V1, is being measured to the reference node. So again, Kirchhoff's current law says all of the currents entering or leaving a node must equal 0. So all the currents that are entering this node coming in to V1 must equal 0, or all the currents leaving the node, in this case V1, must be equal to 0. So we have to sum everything either entering or everything leaving. Personally, I like to do everything leaving because it's you're starting as your node, the node of interest. You're starting here, and then you're just subtracting the node that you're leaving to, and then divided by the impedance in question. Yeah, so let's go ahead and start that. So our first element is this 10 ohm resistor. So we got V1 minus 0. This is the other node in question. So it's just V1 divided by 10 ohms. So we have the current that's going through here, going from V1 to the reference, plus we've got the current going through this capacitor to V2. So that'd be V1 minus V2 divided by minus J5 ohms. And you add that to the current that is leaving V1 in this branch, which is minus 2 because it is opposite of this current direction because this current's going into the node. So it would be leaving would be minus 2 amps with a phase shift of minus 90 degrees. So writing that all out, we end up with minus 2 phase minus 90 degrees. So this branch here plus the V1 over 10 plus the V1 minus V2 minus J5. All of that must be equal to 0. And we have V2, similarly, we have the minus 1.5 amps, phase 0 degrees, V2 over J10, and V2 minus V1 over minus J5. Now that we have our two equations, and both of these must be equal to 0, we just simplify these equations. We're going to put them in terms of V1 and V2, and we're going to use a similar method that we used before. Now you can solve this algebraically. You can solve V2 in terms of V1, and then insert that equation into the second one and solve all in terms of V2 or solve all in terms of V1. It's just simply two equations with two unknowns. Now I'm going to show again using the matrix method, which seems to work well because it is independent of the number of equations. So if you end up with 6 equations with 6 unknowns, you can solve just as well as you can solve with 2 equations and 2 unknowns. So in this case, we have 2 equations with 2 unknowns, and we need to solve and get everything grouped together. So get all the V1 coefficients grouped together. In this case, we have 1/10 and minus 1 over J5 ohms, or excuse me, 1 over minus J5 ohms. And then so we just follow the math through, and we end up with 0.1 plus 0.2J minus 0.2J. Then for the second row, we have minus 0.2J and then 0.1J. So you multiply V1 here, we get 0.1 plus 0.2J. For V1, add that to the minus 0.2J for V2, and then so on and so forth for the second row, and that must equal minus 2J because of this right here. You convert over into the rectangular form, and then the same thing here. We have 1.5 coming over, and if you follow the math on this, these two equations are equivalent to this. And then we just need to apply A inverse times B, with this being our B vector here. And we end up with the X, which is V1 and V2, which looks like this. And we end up with V1, V2 is 14 plus 8J volts, or 16.12 phase 29.74 volts, which converted over into the time domain. We're asked what V1 of T was. It's just 16.1 volts cosine. Again, omega was in the original setup was 100 radians per second, so that carried over 100 T plus 29.7 degrees. If you're asked for what V2 was, V2 of T would be 28.01 volts cosine 100 T plus 2.04 degrees. So in summary, we looked at nodal voltage analysis and steady state AC circuits. And again, the only difference between the analysis that we have been doing so far with DC circuits, doing nodal voltage analysis there, and now with AC circuits, is the introduction of phasors. So you need to be comfortable in converting the sources and converting the components into their proper impedances and or phasor form, and then applying the same process that you did with DC circuit analysis now to AC circuit analysis. And then make sure that when you are asked for something of t, like in the case we were just looking at V1 of t, that you actually give the answer in terms of the cosine omega t, that you actually give it back in the time domain and not in the phasor domain. So again, if you have questions on this, which I'm sure you should have some questions on it, usually most students do, please come to the Q&A session and or my office hours to discuss.